Well, I will get started. Thank you for coming to my talk at the very end. I'm tired. Got here yet. So, I start with an analogy from meat space, right? You know, cyberspace is where we all work, but meat space is where we all live. And in meat space, so like Provenance, what is it like? When you buy something physical, you get some property. You get some information, maybe about where it was assembled. You say it's a product from Mexico on the box. Where its parts came from, maybe you get some organic criteria or sticker on the package that lets you know it met some criteria or another. If you get like a physical good from Amazon, sometimes inside the box you'll see inspected by quality inspector number 13. And so you know some things about where this product came from. A thing that people are super familiar with is like the ingredients list, right, on bag of chips. And that is not quite like Provenance, like what I want to talk about today. SBOMs, software built bill of material, is much more close to that. Like if you're looking at an artifact, what are all the open source components and dependencies that go into it? You see that in SBOM, and it's related to the idea of provenance, but not the same. Provenance is more about where did the artifact itself come from, not so much what went into it, but what were all the things that happened to it along the way. So with software artifacts, we generally don't get that information. Like if you're consuming anything, like it's really, really hard to come by. SBOMs are becoming more popular, like Python packaging ecosystem recently passed some patents about providing SBOMs for Python itself. You'll see it from some vendors. But the provenance information is not a thing that we've come to expect. Welcome to the end of the day. We're talking about provenance. Software provenance. For a software artifact, right, like if you are downloading something, like a Python wheel from Python packaging or anything you get from a vendor, you'll get a binary, you'll get a tarball, but like clear information about where the sources for that came from are not a part of the APIs, they're not a part of the artifact. Typically, this is becoming more so the case sometimes, but definitely less so in the past. We talk about like Maven jars on Maven Central. Are these compiled outputs of a jar that was built on somebody's laptop or maybe built in a build system somewhere if we're lucky for that jar? But being sure that you can actually recompile that same jar from that source is like an act of faith for most people consuming jars. And nobody consumes the sources. Everybody's consuming the pre-built jars that are distributed. Same with Python wheels, right? Are built from some source. There's an S-disk that often comes out from the source distribution, but knowing that they're the same, one really relates to each other, you have to like open them up and inspect, and nobody has time for that. Knowing how it got there, did it come from a laptop or from some build process? Knowing if any checks were run against it, you just basically have to go and look at the upstream and like analyze their processes and read their README to figure out what they do as a part of what their project is to know. Know something about that. We don't have like a standard for transmitting that, or I guess where do we? I'm jumping ahead to my next slide, but why does this matter, right? Like supply chain threats are things, supply chain attacks are a thing increasing over time. Notable ones are like SolarWinds, where the build system itself was compromised. Github and their bash uploader script. The PHP community had an issue where they were hosting their own Git servers away from GitHub, and the Git SourceForge that they were operating got compromised and ended up with malware getting into PHP, and they since moved to GitHub. But all of these are like different kinds of supply chain attacks that we don't have any visibility on, short of just trying to communicate about them informally and dealing with them. This is a diagram from the SALSA documentation, so the text at the bottom, supply chain levels for software artifacts, SALSA, with an attempt at developing a standard for making these statements about software provenance. If you have an artifact, it's a way to say, communicate what are all the things that happen to it along the way. And in their docs, they have this diagram just depicting the different threat vectors. What are all the different places in which an attacker might find a way to get something into a software artifact that you're consuming downstream. We typically really only think about, historically or classically, about security here at point H, right? That's the signature. If you're downloading something, if one of your peers is downloading some software and they're like being like, let's say, careless about it, and then they're not checking the digest of that binary against a signed like SHA-SYN thing, like people will criticize each other, oh, you're being careless, you should always check your signature. But it's really, that's the only attack that you're mitigating with that kind of practice or behavior. And to that point, traditional software signing, what does it tell you? If you have a signature on an artifact or a signature on a JSON file next to it, you can like deduce from that signature who signed it, right? You have their public key information in the signature, but you don't know what they were trying to tell you by signing the artifact, right? Like we typically just interpret this on like a high level. It means the artifact is good. They meant to give this to me because it's signed, but there's no way for them to express anything else other than this kind of like general notion of, well, just this fact that they signed it, and that's it. And attestations. So this in toto attestation framework, there's a couple different layers here. In case now I'm thinking about my slides, I mentioned SLSA before. There's a building up of layers here where at the base is this in toto attestation framework, which is a way of making statements in general about software artifacts. It's this JSON schema for describing and encoding expectations for how those things should be signed and how they should relate to software artifacts. So it's pretty abstract and maybe difficult to use on its own, but just think of it as a way to make statements in JSON that you can expect others should be able to decode and interpret in some way. There is, like it says on the slide, the identity of the person who's making a claim. There's the content of the claim itself called the predicate. There's the subject, the thing that the claim is about, and then all of this cryptographically signed. Right? Just like a signature that you would expect to find on a normal artifact, except this is a signing of the attestation itself. It looks something like this. You generally see everything, well, encoded in this base64 encoded statement. The payload type letting you know that it's an in toto attestation. Inside that payload expanded, you see the subject and the predicate. And I'll also show some more specific examples of that later. SLSA provenance is this description, again, of a statement about how the thing was built. There are other kinds of attestations that you can express in toto, but which are not provenance attestations. So SBOM is one of them, right, the ingredients label. Also, vulnerability scan and attestations for a scanner to say, I scanned this at this time, I found these things at this time, and publish that in association with the artifact. Test results, if you have functional results or like JUnit results, is a way to encode those in like an in toto attestation and publish them with the artifact. And if you're thinking about this, and I've been framing it this way the whole time about like consuming artifacts from the open source community, like that seems less relevant. Like, why am I going to download the JUnit results of some library when I'm pulling it in? But think in the context of like a large organization, like an enterprise or something like that, and you've got multiple departments, maybe multiple security zones, and you'll be transmitting information downstream, so the downstream consumers can be rationalizing about an artifact. Does this meet the expectations that I want to see as it's entering my quality gate? And having those things expressed in a standard portable way associated with the artifact is a really, really nice property, right? That even as it makes its way to production, it's still then inspect after the fact. Wait, is this still the thing we want to be running? Did it pass its test? And at what time did it pass its test? Right? Bespoke APIs in your organization solve that problem today. Everybody knows you have bookmark the Jenkins instance to go and debug this stuff. But having a machine is a little field. Opens new opportunities. So provenance, predicates in practice. Maybe not time, should be good. Like I said, we need to copy and run this. These are commands that run. Trust me, or should I run? These are commands that run. So you can put anything in a predicate, right? This is hello world. It doesn't look like a real, what you'd expect to see. But you can put it in predicate.json here. And then let's say I built a container image with that. Quay.io rb/test, get the BSides, and I want to test something about it. I can use the cosign tool. It comes from the Sigstore project. Running that, it's fun. Maybe I should run this. Yeah, that's more fun. Okay. I have opened a terminal here with already predicate.json prepared. Yeah. And with predicate.json, I'm going to go back and copy this. Do I have all my backslashes? And when I run it, the cosign tool is cool. You can, in the mode I'm about to run it in, that's really small, I'll make it bigger. In the mode I'm about to run it in, it's using what the Sigstore community that produces the cosign tool called keyless signing, which is a little bit of like a marketing hype thing. There's really a key involved at the end of the day. But what it's going to do is it's going to notice that I haven't specified an option where I say I want to use this long-lived key, this GPG key, to sign this stuff. And so it's going to default to its fun behavior, which is it's going to prompt me to go through an OAuth flow. proving that I am who I say I am with respect to some identity provider, like an open identity provider. And in doing so, it will create a short-lived key, valid for about 5 seconds, and use that to sign my attestation. Later, when we go to verify, that key will have expired. But we're not going to be trying to verify things in terms of the key's validity. We're trying to verify in terms of, was there a thing that was signed provably that that I had access to that OAuth identity at the time I made the signature. So I run. Oh my gosh, it's too big. It's going to jump me over back to my browser, where I prove I can log in with GitHub. And in so doing, I'm back using payload predicate.json uploaded. There are some other architectural pieces involved here I can't unfortunately get into. There's a transparency log where you can use it to detect attackers who have compromised access to the OAuth servers by seeing evidence of them signing. Like if you lose access to your key, the transparency log makes it such that they can't hide. Right? They have to expose themselves even if they have compromised your trust root. But so that's that command. Close this and get back to my slides. The second part being verify attestation, and all we're going to do is get back the thing that we saw. I'll paste it, pause for a minute, and then talk about it. So verify attestation, we are going to use certificate identity of ralph.ian@gmail.com, it's me, and a certain certificate OIDC issuer that's as attested to by github.com, login OAuth. If this image, we can find an attestation that is signed matching these properties, then pass. This will exit with code 0, right? Otherwise it'll exit with code 1 saying failed verifying attestation. And furthermore, it'll print it to standard out. We're going to pipe it through JQ to kind of like unpack that base64 encoded blob and then just look at it. In doing so, let's see, I'm sorry, I have to make it smaller, but it's not that big. What we see is an in toto statement. You can tell by the type at the top, certain predicate type. The subject is that image with the description of the badges that I attested to at that time. And then finally, the predicate that here's my little generator, which is not all that exciting. But this is the kind of tool at the bottom of the attestation step. I guess it's one below. I was talking about in toto before is this abstract framework for making attestations. The cosign tool gives you a way to work with that, and we'll move up next to SLSA attestations, which are these statements that are meant to describe supply chain processes. Right? That's the more interesting part, I think. So we'll switch, next slide. I want to talk about 3 different ways that they can be generated. There's more ways. Anywhere that you can use cosign, you can generate these things. You just have to have it, be able to construct the SLSA provenance statement by hand, which is cumbersome. But GitHub Actions has GitHub put out an action, attest build provenance, which uses cosign under the hood to do exactly this. So when you build something in a GitHub action, in a GitHub workflow, and you call this, invoke this action, it will use cosign to generate one of those attestations, but with the structure that describes the GitHub workflow that's doing the building. So at the end of the day, you've got some ball pops out, and you've got a statement signed cryptographically using that OIDC flow from GitHub that says, this GitHub workflow definitely built this artifact, and it came from this repo. And so again, that's the bottom. You get information about the commit shot, the repo URL, the workflow files, and the inputs that were provided to it. But a problem that you'll find with the GitHub attestation metadata is that it doesn't really tell you anything in detail about what happened in that build at that time. Meaning, like if you're referring to actions checkout v4, it's just absent in the attestation. It's absent entirely. You don't even see it there at all. But for what I would want to see is actions checkout v4 and the particular git ref of that action at that time. Right? So when you're looking at an artifact, you can see, if we learn later that actions checkout v4 was compromised between the state of these hashes and so on, you can extract that from the provenance. But with GitHub provenance, you don't have that information. And we've tried hacking around GitHub's APIs to see if we could pull that information out, and we don't find a way right now. So you GitHub to do something like that, I think, to make that information available. You want to see one? Let's do it. Check my time. I only have 6 minutes left, man. Here. This is my buddy Louis' image built in GitHub. And I'm going to run this alternative command to grab the blob out of the registry. corresponds with the attestation and just explode it here. And so in full, I guess it's kind of small, but this is the GitHub attestation. It has what it says. We know the artifact we're talking about, that's the subject. We have this predicate that goes from here to here. We have some information on parameters that went into it, and we know which repo and which commit it came from, but nothing more. Nothing about that actions and v4 action that was used. A second thing about the GitHub method that's weird is that the key that is used to sign the attestation is essentially available. But the signing material is not quite this key. Right? The ability to perform that auth flow to prove that you are the GitHub action that it gets to sign with an is available to the GitHub action. So it can lie about itself. It cannot build an action. And then it can sign statements about it, or it can sign statements about outline or something. It's not that it can necessarily has rights to push that attestation to sit next to the proper outline image that everybody uses, but it still feels weird, right? There's this vector that from within the build system you can use the signing key, depending on what you've committed and pushed in and you're asking to be built. In the system that me and my team work on, we're using Tekton, which is the CI/CD platform for Kubernetes, and this is the way you describe a task run. In Tekton, asking for a similar thing to do a git clone, passing in some parameters with other build steps, let's say the committer. The cool thing about this system is that in Tekton, there is a controller that runs next to the main part of Tekton that's watching the Kubernetes API for the evolution of these pipeline runs. Like you see the evolution of the GitHub action in the GitHub UI, in the Kubernetes cluster, you see these pipeline runs, these Tekton pipeline runs evolve. And this controller is called Chains. And Chains' job is to, when it sees that finish, to describe, capture the state of the pipeline run, time it finishes, generate a salsa provenance predicate for it, and push that into the registry, along with an artifact that it sees has emerged from that same pipeline run. And so you don't get that problem that GitHub has at the end, that the key is available to the build workload. You can't force that system to lie about what it's seeing. It's a neutral observer, right? It's like outside of the data plane of the build. Also, it just so happens that the detailed material, the materials are very detailed. And if we look on the next slide, you can see an example. And this is the and it's going to be too long, right? If we like pipe this through word count-l, can you see that as the bottom?
Yep.
Yeah.
2396.
This is many lines of JSON, right? More JSON than we want to see. I guess I don't know what to refer to in it, but you see all sorts of details about every task in the process here. It wasn't just one git clone task that ran. There were really 18 tasks or whatever that ran in this pipeline doing various things. But the point is that for each of them you have the resolution all the way out to the digest of every image that went into it and every task that pulled those images in. It's very detailed. I'll jump off of that and back. There's one last tool that's cool that I have not much experience using called Witness. And I see it's becoming popular in the GitLab CI/CD community. It, like the GitHub one, has the problem that it runs inside the pipeline, so the signing key material is available to whatever your developer is passing in, assuming you can't trust your developers, or that maybe that the repos get compromised and so on, they sign things in a new way. But it has a really cool set of plugins for figuring out what's happening in the build environment right around the build, capturing all the environment variables, the states of files, the digest, and everything, in a way that Tekton Chains doesn't have that information. It's just kind of looking from outside the process. And these are all the things I saw run, not here's all the nitty-gritty details of the file system. I have run myself out of time. I had a whole section I wanted to talk about my project, but I got to blow through it. I'll say the point I want you to take away. Here, maybe this is it. With these attestation things, you might hear, like with S-bombs, that oh man, I gotta start producing S-bombs. I gotta start producing Provenance stuff in my pipeline because somebody told me I have to for compliance reasons. It's just a thing we got to be on. But if you have those really detailed attestations and you can trust them, you can do cool stuff that you couldn't do before. We use it for policy gating every this time. So anytime an artifact is coming through, we look at that super detailed attestation and we say, okay, first of all, did this come from any of our trusted repos? We need to check. And second, were the tasks that were used to clone, prefetch dependencies, build, and scan, did they happen in an order in which there were no other tasks running in parallel that had access to modify things in or out? Right? And we can describe all that in a readable policy that we use to analyze it. And we build up this body of policy over time, it gives us, in this next one, this crazy flexibility, right? Because we can, in our older systems, we always made it the case that to do an insecure thing was impossible, right? And this created an incentive for teams who wanted to innovate and try new things to work around the system. So we had shadow IT of shadow IT. In this system, we can permit an insecure thing to happen in the build system, but still gate it at release time, which then, depending on like a business trade-off, but do we want to allow this thing to ship, even though it can't do a hermetic build? It's going to be hermetic build. Like that's a requirement for us. Maybe a new language, package language manager we can't support yet. Well, we can say yes to that without it having to create its own shadow pipeline and these like layers of security and technical debt. I really like this fact. There's also a scheduling element to it too, which is in the policies we can put dates on rules, so we can put them in place and say this goes into effect in 60 days time. And all of our developers are receiving feedback in their CI about, okay, this is valid, you can ship it today, but you're not going to be able to ship it in 59 days, 47 days, and so on going down. We used to have to do these flag dates, right? And big emails, everybody get ready, have it built secure by June 1st, and invariably people would break, and we all have things. Those are things I like about this. And that's it. Thank you for coming to my talk at the end of the day. If you have questions, I'd love to talk about it, but I know you don't. Thank you.
Probably one question. So is it always tied to a build? Like, is that where the attestation and signing happen? Is it always build versus commit? I know you talked about it tied together, but is it really focused on the build process? An artifact is built and that's what it's tied to?
Yeah, I think that there is, for Salsa in particular, it's been focused on the build, but they have these different tracks of the specification they're building out, and there's one for source attestations that's like in draft right now that they haven't published. The tooling Cosign definitely supports that kind of behavior, like a developer using Cosign to sign their commit, saying you did a two-party review of that or whatever. But incorporating that into the broader Salsa chain is still coming.
Gotcha.
Yeah. And the idea that you can sign something well after, I think that's totally in place too. You could build and ship, and then later, publish an attestation that's this summary kind of, it's called a VSA, verification summary attestation. Say, now on July 1st, even though this thing was built a long time ago, it still meets our requirements today. You can put that in the registry, kind of stack up these VSAs. Or this ran in staging for 3 days, meeting our soak time requirement. Add another attestation that casts that criteria. So no, it's not just build.
Gotcha.
But build is what's most interesting. Yeah.
So could you have in that pipeline a release that you have for like developers, and then a release that you'd have that meets all the security requirements that you might ship to like the DoD?
Let's say yes, the developers can hack up in their own pipeline ways of building that do not meet the requirements. And the only time that matters is if they would try to release it to our customers, at which point we would block it. Or try to release it to our managed SRE environments, at which point we would block it.
Okay.
There's slightly different requirements and policies for those two things. Cool. All right, thanks everybody.
We're all going to do it, right?
Yeah.